Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will be discussing on the phase transformation and thermodynamic aspects of nanomaterial. Since the size or the length scale of the structural units are very small, so how does it really affect on a coarse grained or coarse microstructure with a nanostructure? So, this is one of the major topic and of our interest. Now, first let us start with the thermodynamics of nanoparticle. We all know about the Gibbs free energy and Helmholtz free energy. In order to just to separate these two terms, I write here as a Gibbs free enthalpy, okay, and G is basically the net free enthalpy with the enthalpy, that is the internal one, minus T is the temperature and S is basically the entropy of the system. So, here since in a nanomaterial we have a large surface area, so we must introduce another term which will take or consider about the surface area and surface energy. Okay. So, let us say here gamma is the surface energy, specific surface energy, and multiplied by the surface area. Okay. Then we will get the total energy. Now, if we consider that, then we can simply think about the difference of the surface energy in a solid and the liquid state. It should be the same order as the magnitude during melting phenomena. Okay. So, here just have a look in the right hand side diagram. We have plotted here particle diameter versus the enthalpy or surface energy. They have the same unit. Okay. So, in case of a surface of the solid, it is area of the solid multiplied by the surface energy of the solid. In case of the liquid, it is basically the area of the liquid and the gamma of the liquid. Okay. And here the green line is the surface energy of the solid with particle size using this equation, and here this is basically the surface energy of the liquid. Okay. And the difference is basically these two surface energies are shown here, whereas the enthalpy of melting is lying here. So, enthalpy of melting for a particular system is constant at the very first assumption what we have. But what is interesting that if the particle size is below 10 nanometer, then these two energy term goes higher than the enthalpy of melting, which is looks like somewhat contradiction than what we thought. So, for particles that is smaller than the 10 nanometer, the surface energy of the solid and the liquid state is higher than the enthalpy of melting. Means I have solid substance, I am going to melt it, and this gives us some further motivate us to think about this matter, why such thing happen actually. So, in that particular aspect we can think about the let us say the heat capacity of the nanoparticle. This is also another very important aspect, and we all know that the heat capacity at constant volume du by dt okay, at constant volume, and then we can simply consider u as derivation with temperature. So, that will be delta S by delta T. So, during transformation temperature T is constant. So, here very first assumption that we have considered here as a liquid crystal, okay, a linear crystal. Here this linear crystal basically means that the atoms are arranged linearly, and if we consider the vibration at 0 k, then yes, it is almost stagnant, but just above 0 k definitely lattice should vibrate and some wave is linked with that vibration. Now, the question here, which wavelength or frequency can be accommodated in this particular linear crystal, or let us say linear arrangement of the atom. If we consider that the distance between these two atoms is a, like a simple when we consider lattice parameter, okay, and then the crystal size, the linear crystal size is L. So, I have n number of atom, let us say. So, n into a, that is the relation we get. Now, we can vibrate this particular lattice, linear lattice, when the lambda maximum that can be accommodated to vibrate, that is basically the 2 of L, means I can have such a wave, and then I can vibrate it, and the smallest wave that will be basically here, wavelength will be like this. Okay. So, the whole lambda is basically 2 into a. Is it clear? Now, let us say if we consider frequency as nu and the elastic wave is c, then we can simply make this in terms of nu. So, nu is basically maximum is equal to c by 2 a, or nu minimum is nu by 2 n a. Okay. This is the same equation. So, since each and every vibration is linked with the net thermal energy E, so here we can make a summation of all the different vibration energy in the linear lattice. How to do that? Simply E is the summation of nu and h. So, here each of the energy is basically the Planck constant h nu. Okay. In that case, you will agree with me that lambda become, this is the lambda which is basically your n a by 1 or 2 or 3 and so on. So, this will go on up to n, or let us say if n is very small, then we can think about 2 L by 1, 2 L by 2 and things like this. So, similarly, we can also get the nu value. Here now, let us consider this is the linear size. Now, I am going to reduce this size. So, let us say here. So, I have a linear crystal of this size instead of this. So, now I have basically 4 a size. In that case, the lambda maximum will be larger or smaller. So, lambda will decrease, there is no doubt. Then lambda max will be this and lambda mean will be this one. Okay. Lambda mean will not change, but lambda max will change when we will decrease this linear crystal size, okay, or when n value reduces. Now, what is the meaning of decreasing lambda? It basically means the energy is higher. So, the reducing the particle size, the energy of the vibration with the longest wavelength, which we are talking about lambda max, that energy basically increases. So, energy will increase because lambda is going to be shorter. Now, as the vibration of the excited that primarily at low temperature, therefore, a reduction of the heat capacity at low temperature is expected. It basically says that if we decrease the particle size, then simply there will be a reduction of the heat capacity. So, this is let us say just a mathematical formulation of the idea of reducing, let us say a vibration in a linear crystal, the size of a vibration. And so, this is a model that was told by these two scientists Sakov, and this is simply a model calculation. And using this model, we have plotted here the particle diameter with the heat capacity. You can see as we decrease the particle size, it basically reduces. However, when it is below 1 nanometer, means 1 or 2 atoms are basically arranged in a linear fashion, or 2 atom is arranged in a linear fashion, then there is a sudden jump of the heat capacity. The question arises that why such thing happen. So, this is a calculation on indium oxide, where there is a decrease of the heat capacity with the decrease of the particle size, that is observed. But people are interested in this region, that why there is an increase. Now, we have realized that if we decrease the size scale or length scale, then there will be more number of surface atom. The more number of surface atom means the atom has more degrees of freedom to move, and therefore, the heat capacity should increase. So, this is a simple model that seems to have two different questions that arises into our mind. So, one, there is a decrease and then there is again increase. So, this is the two trend that we can observe here. Now, let us look at the real experimental data that people have measured. So, here the experimental data for, let us say, a metal is shown here, and this metal is basically a coarse grain copper and a nanocrystalline copper. You see just the opposite trend, means here there is a temperature, at any given temperature you see that in case of a coarse grain it is lower than the fine grain, means the heat capacity of a coarse grain material is lower than the heat capacity of the Cp. So, Cp value in a nanocrystalline material with a larger number of surface atom increases, right. So, the large number of surface atom should be considered in that model, the model of basically Sakov models that fail to explain such situation. Very similar situation has been observed in case of palladium also. Here the heat capacity of a nanocrystalline palladium is higher than the coarse grain palladium. So, now let us continue whether the system that I have shown you, that is on metal, is it valid in case of ceramic? Yes, it also valid for ceramic. These are measured data that I show you in case of alumina. So, the red color curve is, let us say, for the nanocrystalline alumina, and the green color curve is from the coarse grain alumina. This is a ceramic system. Therefore, the situation is very much simplified or generalized, that the surface atoms must be considered when thinking about the heat capacity in a nanomaterial. Now, let us look at the phase transformation behavior in a nanomaterial. Is it similar, or whether large amount of surface really helps or retard the transformation? That is basically the question. In case of nanomaterial, before going to that, let us consider that there is a parent phase which is termed here as old phase, and the product phase which is a new phase. So, this is the product and this is the parent phase. Now, this is undergoing some phase transition at some temperature, and so the parent and product phase they have the large surface area if we consider it as a nanoparticle. However, the basic fundamental equation of thermodynamics that says that U internal energy of the old phase, means the parent phase, minus T into S into the surface energy term should be considered like in the earlier case that we have considered. They are in equilibrium means basically these two sides are the same value or 0. Now, here the difference in the internal energy of the system is basically U of the new phase minus the old phase. Similarly, the entropy change is the new minus the old phase. Okay. So, under equilibrium, now if that is the case, then under equilibrium the net free energy change should be the delta U minus T, which is the transition temperature into the delta S, okay, and the difference of their surface energies. And now, you already know that area is equal to 6 m by rho into d, that we have discussed in the last class. So, if we decrease the grain size or the particle size, then surface area will increase. This is the molecular weight and this is the density term. So, we simply take these area term and put it here. So, we have the same term, that is gamma nu, and here is the gamma old. So, these are the same term basically came. So, now the net change of the free energy or enthalpy, whatever you call, is somehow linked with the change of the internal energy, change of the entropy of the new phase, and then the difference of the surface energy term. Now, if we take this equation, then we can also write down d nu by old is the rho old by rho nu to the power 1/3. This is the ratio. Now, I am simply putting this value and here, okay, and then see how the equation changes. So, if we put that, then we can simply write in a more simplified way that the transformation temperature when it is under equilibrium, okay, that will be basically delta U by delta S. We have divided by delta S actually the earlier equation. Please have a look once again. So, here we have divided by the delta S term. So, this is the delta S transition. So, this one goes, so we get T free, and then here also delta S trans, and here is also delta S trans. Okay. So, this is the idea that we are talking about actually. Now, so we get basically such a condition where the 6 m rho by d, okay, which is basically the total energy of the surface, and then you have the rho and basically the delta S. Now, once again what I am trying to do, that for coarse grain we can think about the transition delta S, which is T coarse is equal to delta U of this transformation divided by delta S transformation. So, taking this delta S and I am replacing this delta S by basically T by delta U transformation. Then I will end up with that the change of the temperature, which is basically T coarse or minus T transformation because of the smaller size of the particle, I will end up with such a equation. Okay. So, where this is the same part and this is also the same part here. So, it basically says, you see that the relation of delta T means change of the transformation temperature with, let us say, the particle size. They are inversely proportional. Okay. So, means the particle size before and after transformation, if it is negligible, then change of T is inversely proportional with the D. Okay. So, once again I write down the same equation as delta T here, and then I am basically making that gamma term T coarse both are there, U and D is there, and rho. So, this 2 term, okay, this 2 term I am putting as a alpha here, the whole term. And let us say here this is a term which I call as a 1 minus beta. Okay. So, this whole thing we basically consider, and then we can directly link that the transformation temperature change is inversely proportional with the d. So, this is called as a Thomson's law. Now, is there any application of this Thomson's law, and can we look at some real examples? Yes, that will be very nice to see such an example, and let us have a look. I wrote here the same equation as delta transformation temperature change, which is equal to alpha into gamma T course by delta U into d, where alpha is equal to 1 minus this term 2/3, where 1 minus beta is there. Now, let us consider about the melting temperature. In case of a melting, the change of the transformation temperature, if you look at this equation, if this part is less than 1, then definitely it will be inversely proportional with d, and delta T will be positive and it will increase. Delta T will increase, not means that the transformation temperature will increase, it will basically decrease. So, in that case you will see that melting temperature should decrease with the decrease of the particle size. Okay. So, the change of the transformation temperature will increase with the d, and let us see the real measured values of melting temperature in case of aluminum. So, here Eckert was measured this melting temperature by the melting temperature of aluminum, and it has been shown that this is the melting temperature of bulk aluminum, but if we decrease the particle size, then there is a decrease of the melting temperature, and it is not very small, it is quite large. So, this is like 930 to 830, 100 degree there is a decrease in case of a aluminum. Okay. This is given in Kelvin. Now, if we consider only this part, how does it affect and what is the value of beta, because I said beta should be less than 1, then only we will be able to decrease the transformation temperature. So, here let us say in case of copper, gold and silver, we see here the gamma liquid by solid. Okay. This is the characteristic temperature. So, solid by liquid and gamma rho solid by liquid, and ultimately this net term, okay, that is 0.9, 0.93, 0.89. Okay. That I said that it is less than 1, and then you will get a positive value of delta T transformation temperature. In that case, there are also people who have measured actually the U melting, because here we can derive basically the effect of parameters on delta T, where there are two parameters that is very much important. Okay. We definitely should look at the surface energy term. However, we can also measure the enthalpy of the transformation, and then this is with 1 by d. Okay. So, nanometer inverse. So, this means in this size the particle size is decreasing. Okay. So, and this size d is increasing. Okay. In case of a metal, the same actually, here this is also measured by Eckert et al, and so they have shown that the U melting decreases with the decreasing particle size. Okay. So, you can see that the reason not only because of the effect of the particle size, but the net enthalpy required for phase transition during melting is also less, because you already have a higher amount of energy in the system because of the large number of surface atom that assist during the phase transformation process. Now, the question here, we have shown you in case of a metal, but how the system react when it is a ceramic system. In case of ceramic system, the very well known zirconia is very much popular. So, zirconia has a phase transition, that is from monoclinic to tetragonal, and the stabilization occur when we add yttria in the system. So, yttria can be added to the system in terms of a coarse grain particle, or let us say very fine nanoparticle. So, people tried to measure the transformation temperature when the transformation temperature of this monoclinic to tetragonal and its change. So, this is the particle diameter and this is the percentage of weight percent of yttria from 1.5 to 0. So, in case of 0 percentage yttria, if the particle diameter decreases, then the transformation temperature also decreases. Now, here if we add some yttria into the zirconia, and zirconia has a rather smaller particle size and decreasing particle size trend, let us say from 140. So, this is the zirconia size that also decreases. So, if we decrease particle size, the net transformation temperature also decreases, means I am decreasing this value and there the delta T is increasing. So, this is the delta T. So, this is the delta T transformation temperature. And so, very similar situation, if you keep on adding, let us say different amount of yttria. So, here is a higher content of yttria of 1.5 weight percent. So, we can further decrease the transformation temperature. So, it basically says that if someone really want to stabilize zirconia at much lower temperature, then we not only should involve yttria into the system which stabilizes the zirconia, but further if we decrease the particle size, then also the transformation temperature will decrease. So, these are the very interesting information about the thermodynamics and phase transformation characteristic of nanomaterial, and we will discuss this nanomaterial and the other relevant important topics in the next class. Thank you.